All right. Okay. Hi all. Tonight we're meeting to deal with questions on gravitation. 3 specific questions. The first one is page 167, question 5. The first part of the question asks, state Newton's law of gravitation, and we know that that law says that when you have two masses, the gravitational force is directly proportional to the product of the masses, and it's inversely proportional to the separation squared. So again, that's pretty straightforward. We want to, however, look at this part of the question. We have the Earth and the Moon. And clearly there's going to be a gravitational force between the Earth and the Moon. And they're asking us to calculate the mutual force of attraction. Now, with this question, they want to find the mutual force of attraction. We certainly would need the mass of the Earth and the mass of the Moon. And the data for that is available right there. Mass of the Earth, mass of the Moon. On the front page of your handout, your past papers. All right? Right. So as a result, we can very easily just put in the numbers g m1 m2 over r squared. I think I already did the solution to that. And this is what it's looking like, the calculation for that part anyway. I'll just make it small. So, all right, so we simply, substitute for g m1 m2 and r squared. This r is 3.85 by 10 to the 8. The 8 is kind of blurred here, but that's what it is, 8. It works out to be a force of 1.98 by 10 to the 20 Newton. Again, that is pretty straightforward. It's just a matter of substitution. They then ask us for the speed of the Moon, assuming that its orbit is circular. Now, from what we've done in class, the gravitational force is equal to the centripetal force, and the centripetal force is equal to 2 things. Let us just write it for visual reference. The centripetal force is equal to m v squared over r, or it's also equal to mr omega squared. Sorry for the horrible writing. The control, this is a pain. mr omega squared. And that is the centripetal force. But in this case, for the gravitation, centripetal force is really equal to Fg. And we have just gone and we found the gravitational force. We've just gone and found the gravitational force. So all we really need to do is to substitute for Fg, 1.98 by 10 to the 20, and use this part of the equation to find V. M again is the mass of the Moon, because this is a centripetal force acting on the Moon as it moves in the orbit. So once we run those calculations, we would get that the speed of the Moon around the Earth should be about 1,020 meters per second. All right, that's okay. Yep. Anybody want to discuss anything there? Just type in the chat box. Can I move on? All right, so we'll move on. The next part, this one is about communication satellites. Let's just clear that. Let's clear that writing. All right, a communication satellite have the same rotational speed as the Earth. They move in a geostationary orbit to provide worldwide communication. Prove that the velocity of a satellite in geostationary orbit. Again, you're looking at the same idea that centripetal force is equal to gravitational force. We said last day that once an object is in stable orbit, the required centripetal force is provided for by the gravitational force. So we start, with that. And you can see by just proceeding by populating the equation, replacing the centripetal force by mv squared over r and the gravitational force by gmm over r squared, we can make v the subject of the equation and get exactly what they want us to get. That the speed is equal to the square root of gm over r. And the next part, t squared is proportional to r cubed. Again, we did this in class just this week. Between last week, Friday, and Tuesday, we did the same identity in class, and we call this Kepler's third law of gravitation. And again, it starts from equating this, but this time, instead of using the mv squared over r, we're going to be using the mr omega squared, because omega has time built in it. Omega we know is equal to 2 pi over t, all right? Omega is 2 pi over t. Again, I will write that to give us a visual reference. Omega is equal to 2 pi over t, right? So we can then replace omega by 2 pi over t. That's it there. The m's will cancel out, and we put the equation in terms of t squared. So t squared is equal to, and we said this was a constant, 4 pi g and m. They are all constants. So if you have t squared is equal to a constant times r cubed, we consider t squared is proportional to r cubed. Up to speed there. That's pretty straightforward. Again, the next one, give a reason. Right, this other part. Prove that the satellite must be placed a distance 6 RE above the equator. Now we know a geostationary satellite, we know its period. So looking back at this equation, we know the period of a geostationary satellite. We know the universal gravitational constant. We know the mass of the Earth. This is the mass of the Earth. So we can simply run this calculation for the period that we know. The period, it must be in seconds, so it must be 24 by 60 by 60. G we know, M we know. So when we scroll down to the next part of the solution, we see that we can run that same equation, as I said, and solve for r cubed. You look at here, r cubed would be gm over t over 4 pi squared by t squared. And that's all I did here. I put gm over 4 pi squared by t squared. And when you find the cube root of this number, you will get this. And they also gave in the question that the radius of the Earth was 6,000 kilometers. That's 6 by 10 to the 6. So all we do is divide this number. You divide that number by 6 by 10 to the 6. And that will give you the number of radii. You divide this. Oops. You divide this number by the radius of the Earth, 6 by 10 to the 6. And you'll get 7 RE, which you might think is a problem because they want us to show that something is 6 RE. But if you look back at the question, they said, prove the satellite will be placed at a distance of 6 RE. From where? From the Earth's surface. This here is the radius of the entire orbit. This is the radius of the entire orbit. So if you were to show an image of what you just described, we will see that the radius of the orbit is from here to here, that's 7 RE. But from the surface of the Earth, the radius of the Earth is RE. From the surface of the Earth, the height will be 6 RE, which is what they want us to show. Give one reason why geostationary satellites must be placed above the equator. We had spent some time in class discussing why the geostationary satellite must be placed across the equator. We had said that if we have the Earth and we place a satellite at any point that is not above the equator, let's say this is the equator here. Let's just say for the sake of argument, that's our equator. If we were to place a satellite, let's say here, when this satellite orbits, its next location, remember the satellite orbits the center of the Earth, after 12 hours, let's say for the sake of argument that we have confined, we know that the satellite must have a period of 24 hours. Let's say the satellite has a period of 24 hours. And let's say this is where the satellite is at 6 a.m. From Trinidad, we will see it north of us. North of us, we will see it in the morning at 6 a.m. But remember, the satellite orbits the Earth, so after 12 hours at 6 p.m., it's going to be somewhere here, because it is orbiting the center of the Earth. So people in Trinidad would no longer be seeing it north of us as we were 6 a.m. We'd be seeing it south of us. And therefore, that could not be a geostationary satellite, because a geostationary satellite, by definition, stays at all times at the fixed point above the equator. That's 10 to the 8th, Sarah. The 10 to the something, that's 10 to the power 8. All right. Right, so that's why, one reason why a geostationary satellite must be a place across the equator. If you place it at any other point, it will be moving relative to the Earth's surface. And once it moves relative to the Earth's surface, it will no longer be a geostationary satellite. The next part, state 2 uses of survey satellites in the Caribbean region. All right, so your type, I did one in class, but I didn't mention a second use. So could you type in the chat box uses of survey satellites? We did it in class. Nobody remembers. Ooh. I wouldn't call GPS a survey satellite, really. Okay, again, I don't think I would call these survey satellites, GPS and telecommunication. I could be corrected on that, but I wouldn't call them surveys. Surveys where they're accumulating data. And yes, Kyra is correct to study the phenomena such as hurricanes and so on. When you look at the weather, when you look at the weather satellites track the weather all the time. And this is not to say that these satellites here they're talking about, they would most likely not be geostationary satellites. If it's conducting a survey over the Earth's surface, you wouldn't want a geostationary satellite, because you may not want to conduct a survey. You may or may not. It all depends on your intention. But these should be confined to geostationary satellite, in my opinion. But certainly, a survey satellite is a satellite that is gathering data about some aspect, all right, across the globe over a large scale. So that's what a survey satellite is. It's gathering data of some type. All right, you can have satellites looking at the Earth's surface, and taking pictures of the Earth in different specific wavelengths. These wavelengths might be able to determine the concentration of lithium and lithium deposits on the globe, so that they could know where to mine for lithium, a range of things. That's an example of a survey satellite. Another survey satellite could be used to map the topography of the Earth, to map the depth of the ocean. In fact, right now there's a satellite orbiting the moon, the dark side of the moon. I believe the name of the satellite is Kyakutake, a Japanese satellite that is orbiting the dark side of the moon and mapping so it will be pretty geostationary. Yes, polar orbits would be suitable for hurricanes and all general weather phenomenon. So the two that I want to mention, I mentioned one in class, it's called the GLOBE project. GLOBE, G-L-O-B-E. Some schools participate in the GLOBE project. They take temperature samples, rainfall samples, and they upload it to a common server, which is then shared by hundreds of thousands of stations throughout the world, and they're tracking the climate of the Earth. This has been going on for a few years now, gathering that data. So the GLOBE satellite and the GLOBE system is one of them that we use in Trinidad actively. And also, if you're interested in the weather and you want to predict the weather for yourself, you can go on to this site, noaa.gov. And there's a whole host of them. These you will be able to see, and you look at the satellite images of the Caribbean area, you will see when tropical waves are coming, you will see when there are cloud formation at different points. All right, so you can check out that. That's one of the survey satellites. I'll call it a survey because it's mapping weather throughout the Earth. All right, so we're 20 minutes into our session, and we're just finishing one question. But I think this last part required some discussion. Okay, good question, Nalini. Geostationary and geosynchronous are two completely different terms. Geostationary is the one that remains above the equator and has a period of 24 hours and orbits the Earth at a constant position, right? Geostationary. Geosynchronous is one that is simply matched with the angular velocity of the Earth. Geosynchronous could take on a whole range of different orbital angles. All right, let me show you what I mean. I'll draw a sphere again. The criteria to be geosynchronous is its period. The similarity. Let's start with the similarity. The similarity of geostationary and geosynchronous is that they both have periods of 24 hours. All right, they both have periods of 24 hours. Again, let's say that is the Earth. Your equator. A geostationary orbit would always be one right here, across above the equator. This is the plane of the orbit. All right? The orbital radius of a geostationary satellite is the number we just worked out, which is, we call it the height of 6RE. Everybody okay with that, right? From the last question, from the same question, 6R. That's the height. But from the center of the Earth is 7R. All right? That's a geostationary. A geosynchronous satellite could take on any angle of orbit. This could be geosynchronous. Again, it must be orbiting the Earth. Oops, let's change the color of that. I'll draw a line. Gosh, going red as well. So an orbit like this, where you might want to call it a polar orbit, all right, like this, is a geosynchronous orbit, right? The criteria for a geosynchronous orbit is that this distance must be 6R. The height must be 6R. And only, but when I say 6 hours from the surface, if you're talking from the center of the Earth, of course, it's going to be 7 hours. From the center of the Earth, the orbit is going to be 7 hours. Okay, so this is geosynchronous. This is geosynchronous. The criteria for geosynchronous is that it must have a period of 24 hours. Geostationary is a different thing. Geostationary means its period is 24 hours and it's orbiting the equator. Polar orbit could be any one of these. Once it's passing over the pole, I guess I would call it a polar orbit, but a polar orbit could be one of these. Oh, crap. Sorry, excuse my language. A polar orbit could be any one of these. You know, a high angle orbit would be considered a polar orbit. But you can Google it, Vishnu. It's pretty easy. That information is pretty easy to find. All right? We have geostationary. I did not make a distinction between those in class, and thanks, Nalini, for the question, because it certainly brings that point to focus. All right, so that's clear. Geostationary, geosynchronous. We have 6 more minutes and 2 questions to do, so let's get on with it. Next question is on page what? Somebody type it. Page 140 something, I know, but I don't remember the exact number. 140 who? Okay. Nobody typing it. Oh, I think I found it. Is that it? Is this it? No. Page 142. Okay, thank you, Nalini. All right, let's go with this question. If my scrolling will happen today. All right, I think we have it here. State Newton's law of gravitation. This question is a real big question. State Newton's law of gravitation. Again, a satellite is circular orbit. To show this, again, I think I wrote this up already as well. Right, yeah, I have it. So that's like it, right? We have Newton's law of gravitation, and they said to show that the orbit is gm is equal to r cubed omega squared. That's the solution there pretty much. All right, so they ask what is the angular velocity? What is the angular velocity of a geostationary satellite? A viewer, when viewed by an observer with satellite, appears to be remain stationary. Find the angular velocity of the satellite. And that what is angular velocity again? Angular velocity is angle swept out over time. And we know that a geostationary satellite, it's the angle it sweeps out is 2 pi, and it takes 1 day to sweep that out. So it's just a matter of doing the calculation. Again, straightforward. What is the what radius would this happen at? And again, we know that gm over omega squared is equal to r cubed. We just got omega from the previous part. So we simply need to put g and m on top, square omega in the denominator, and run the proof, run the calculator. Right? So that is, that's clear? Yep. Move along. Move along. Thank you, Vishnu. Tyra. All right, let's look at the last one. The last one is page 130 something. Again, what page? 130 what? $136. Thank you, Vishnu. Wow. Machine is running so slowly all of a sudden. All right, this is a nice question. We kind of tried to do some of this in class. Right, so the hammer's angular velocity has an angular velocity omega about O. What is the relation between the speed and the length of the chain? Again, we know V is equal to R omega, straight up. Explain why the hammer is accelerating even though it's rolled at a constant rate. We discussed this in class again at the very beginning of circular motion. We said that when the body is moving in a circle, although it's moving at constant rate, the direction of motion is changing. And if the direction of motion is changing, it means the velocity is changing. Tra-la-la, right? Part 2, write down an expression. Okay, so I'm assuming that you all would have tried these questions at home before this discussion, which is the ideal scenario. So again, time is running out and I want to finish all 3 questions before the time is expired. So you can't portion out work and not complete it, and I don't want to go beyond the time. So again, I already wrote up the proof for that, and it's right here. So here we have, acceleration is v squared over r, and they're asking us for an expression for the force. This expression they want us to prove. So we know F is equal to ma. So F is equal to mv squared over r. But from the previous part of the question, we know that v is equal to r omega. So I can find an expression for omega and then replace omega, an expression for r, then replace r in the equation. One of the v's will cancel out with that and I end up with mv omega. That's a little game they want you to play. That's pretty simple to get it done. The next part is about this bucket of water that we've been talking about, why the bucket doesn't fall on somebody's head. Well, calculate the tension the rope and the bucket is at the lowest point. And we said in vertical circular motion, the tension at the bottom would be such that the tension must provide 2 things to the mass. It must provide a centripetal force, and at the same time, it must act and neutralize its weight. The equation we wrote for that was that centripetal force at the bottom would be mv squared over r plus mg. It would be mv squared over r plus mg. Again, the proof is right here, if you can see it. And once we know that, we have m, we have v, and therefore we have r, and therefore we can simply populate the equation with numbers, and we end up with 1740, which is 1700 to 2 significant figures. Again, the data given will allow us to write this answer, but this shouldn't be, mark shouldn't be taken away even if you write this one. The next part is when the bucket reaches the highest point, the string becomes taut. Right, so the string is still taut. They didn't say just taut. They did not have the word just taut. They said the string is taut. And the water does not fall out of the bucket. What forces now provide the centripetal force? The forces providing the centripetal force, as we said again this week, well, that's on the Tuesday class for sure. I don't know if I did it on the Friday class, but if not, we will look at it this week. The forces providing the centripetal force when the bucket is at the top is a combination of the gravitational force and the tension, right? Sorry. The forces providing the centripetal force is a combination of the gravitational force and the tension here in the string. So we could write at the top that T is equal to T is what? mv squared over r minus mg or something like that. I do have the equation in my head, so I'm not trying to get it right. I just want to get this part sorted out. So certainly the tension would be less than when it is down here. Explain why the water does not fall out of the bucket at this point. And we had some little discussion on that. The water does not fall out because at the top, the water and the bucket, they are accelerating down at the same rate. So the water cannot fall out and leave the bucket behind. They're both accelerating downwards at the same rate, which is greater than gravity will allow. Just type that abbreviated form. That's what I would say would be a fair enough answer to this. All right, at the top, the water, the bucket accelerates now at a greater rate than gravity, so the water cannot fall and leave the bucket behind. So there's nothing to be able to pull that water at a rate greater than it's already accelerating. Uh, so that's why the water does not fall. At what position relative to the axis of rotation is the string most likely to break? And again, we said the tension is greatest. We said the tension is greatest at the bottom. And if the tension is greatest at the bottom, that's where the string is most likely to break. Calculate the angular speed at which this occurs. So when they say calculate, you might think it might be a numerical value, but let's see. We don't know the maximum tension that the string can sustain, or do we? I don't remember they giving us what the maximum tension that the string could sustain. If they would give us the maximum tension, then we can certainly calculate a numerical value, but they did not give us the maximum tension. So the word calculate is clearly a misrepresentation. You can't calculate it, i.e. provide a numerical value, but you can certainly provide an expression. So I think this word is misleading. It's very misleading in the context of the question. And this is a calculation. I will put the t is equal to mg plus mv squared over r. And we're solving for omega, the angular velocity. And the angular velocity at which this thing will occur, omega, is equal to the root of t minus mg over mr. T minus mg over mr. That's the only calculation you can do. Since the maximum tension is not given. If you knew this maximum tension that the string could sustain, you could provide a numerical value, but this is as far as you can get, how close you can reach to the numerical value. Okay, well, I think that's a wrap. Yeah, I think that's a wrap. So everybody, I guess I will see you in class on Friday and or Tuesday, and we will continue working. So good night and enjoy the rest of the evening. Bye.